The Earth's atmosphere has four primary layers. The lowest is the troposphere, then the stratosphere, mesosphere, and thermosphere. These layers, particularly the upper three and the existence of ozone in the stratosphere, protect our planet by absorbing harmful ultraviolet radiation. Temperature decreases with altitude through the troposphere, but then increases through the stratosphere. Conversely, the temperature decreases in the mesosphere, and it contains some of the coldest temperatures in the atmosphere. The thermosphere then begins to warm with higher altitude. The thermosphere warms because molecules of oxygen and nitrogen move faster at this altitude and are bombarded by radiation and energetic particles from the sun, causing the molecules to split into their component atoms. Both the speed of the molecules and splitting of the atoms create heat. The atomic oxygen and nitrogen cannot radiate the heat from this absorption, causing the thermosphere to reach temperatures as high as 2,000 degrees Celsius. As the Earth rotates, the thermosphere is exposed to highly energetic ultraviolet and X-ray solar radiation that ionize the atomic oxygen and nitrogen in the thermosphere. These charged atoms form a layer of plasma called the ionosphere. The ionization of atoms can extend down as far as the mesosphere. However, these upper atmospheric layers are still mostly neutral, with only 1 in a million particles becoming charged daily. The density of this ionosphere layer cycles daily. At night, the ionosphere diminishes as the sun's radiation ceases to interact with the atoms in the thermosphere. However, there are still small amounts of charged atoms caused by cosmic radiation at night. A unique property of this ionized atmospheric layer is that it reflects shortwave radio waves, enabling communication over great distances by bouncing signals off the ionosphere. However, variability of the ionosphere can disrupt communication. Solar storms is one such variable that can enhance this layer, even shutting down communication between ground stations and satellites. Solar storms can also send highly energetic particles, mostly electrons, along Earth's magnetic field lines into the upper atmosphere at the poles. Here, they interact with oxygen and nitrogen, causing formation of auroras. Auroras are formed when an energetic electron strikes an atom and one of the atom's electrons jumps to a higher energy level. When the electron returns to a lower energy level, energy is released, often in the visible light region of the electromagnetic spectrum. A deep red aurora is caused by the excitation of nitrogen atoms. Excited oxygen atoms create a green aurora at lower altitudes and a red aurora at high altitudes. A small amount of solar particles constantly precipitate from the magnetosphere, forming a background aurora that can be seen from space.